Let's move on to our singularity. Let's see what we can find out about that. That's a big monster, by the way. Okay, singularity. Okay, here we go. We have this we've been doing lately. That is the light turning corners, and we also talked about the singularity in the last few weeks. And here we have this is a summary of the problem essentially. When they talk about the gravitational lensing, what you have is a star way in the distance, and when there's an eclipse of the sun, somehow we can see that light coming around the sun, as they say, around the moon, and we are able to take a snapshot or film it or whatever. And the question is, how does that light turn the corner, more or less? Yeah, especially if we're talking about particles. How do they do it? And so the way they explain it is with mass. They say, look, the sun is a great mass, whatever that is. It weighs a lot, okay? And it bends space-time. There you see the bending of space-time. And it bends space-time, so now we have a curved surface. And what happens is the photons, the little discrete particles that make up light, they kind of roll or slide around that curved surface. And they say that's how it comes to your eyes, because it curves around that curve. Actually, it's a deflection of the particles, and what is curved is really the surface. Okay, but anyways, whatever the case, that is their explanation. However, when they talk about the slit experiment, where you have light also turning around a corner, they explain it a little differently. Now they're going to have the particles of light, the photons, they bounce. You know, that's not, the slit experiment is not done with mass, with weighing of space-time. What you have is bouncing. And so they have these two mechanisms. One is bouncing and the other one is mass. And essentially they have the same situation, because what you have is light turning around corners, so to speak. So the question, how do you explain that? Well, again, one, in the case of cosmic phenomena, they explain it with mass, and in the case of quantum mechanics, the small world of the small, they explain it with bouncing. So this is the starting point, and the problem comes in there that we're going to introduce that or put it into context of the singularity. Okay, so let's keep going here. The problem that we have with this is that here, if we put a needle there, right, which is produces the fringes anyways, you cannot do it with particles. Suddenly the particle hypothesis dies, because you cannot show how that particle turns the corner around. Let's assume the needle is perfectly round. How do you hit the edge of the needle and have that particle come inwards? And that's the question. That's the whole issue. So you cannot show how the particle turns the corner. And so you can explain, at best you can explain the one on the left, the one with mass, if you can believe that, if you can accept or concede that the sun somehow weighs a concept known as space-time. It weighs time downwards, bends time, and because of that you have a curved surface and the particles are going to slide along that. Okay, if you concede that time is a physical object, yeah, you can understand that explanation. How do you explain the one on the right? How do you explain that the particles turn the corner during the slit experiment if you're going to do it with a needle? And that's a whole issue. The issue is particles can't turn the corners. That's the issue. Does light go around? Yes, light no doubt goes around. But you cannot explain how particles do that magic trick. And that's the trick you got to explain. Okay, so what was the problem with the singularities of both Big Bang and the black hole? Well, in the black hole here, you can see it sucks light inwards, and the Big Bang spits it outwards. So we have a problem with these singularities, because you would think that the Big Bang had a lot of mass, okay, as they say, had a lot of matter crushed almost to a point, which is that singularity, and somehow all the light goes outwards, and in the case of the black hole, for some reason, light goes inwards and doesn't come out in general. Okay, so we got a problem with this because they have a contradiction there that they've never resolved. How can light go into a singularity on the left and spit out on the right? Okay, so that's the big problem we have there. Okay, so we need to understand more, especially the one on the left. We covered the Big Bang on the right the other day. Let's go with the Big Bang on the left, the black hole singularity. How does it pull all this light inwards? I mean, does it suck it in? Is there, Aeolus, the god of the Greeks, he's the guy who's sucking all these particles in? I mean, tell us. Please tell us. In fact, tell us how particles, why? What causes particles to go to a region of lower density where there's less matter? Let's even talk about perfect vacuum. Why would particles move into perfect vacuum? It doesn't happen on Earth here, at least. You have all this air surrounding the Earth. It's higher density on the inside. There's all this empty vacuum, the space out there, emptiness. And the particles of air do not fly out of the Earth. They stick to the Earth. And thanks to that, we can all breathe. But if it's like these people, especially the flat earthers and etherists, all these people who know very little about physics, they say, well, a particle moves to a region of vacuum, likes to move into a region where there's higher vacuum. No, it doesn't happen. And you do not need a container. Space is not a container. Space is perfect vacuum. Space is a synonym of nothing. And the particles around the Earth, all that air, they do not fly out into the vacuum. They stay here where it's very dense. In fact, the more you approach the Earth's surface, the denser is the air. And the farther away you go, the less air there is. Why don't all these particles go out into space? That's what you got to explain. And we're talking about no container. We don't need containers to contain air. Imagine if God had to build a cocoon around the Earth so that the air doesn't fly out. That's what these people, that's people who know very little about physics, about vacuum. They've never dealt with vacuum, so they have very little understanding of vacuum. Okay, so this is NASA, and they tell us what a black hole is. Let's start there, okay? Black hole is an astronomical object with a gravitational pull so strong that nothing, not even light, can escape it. A black hole surface, called its event horizon, defines the boundary where the velocity needed to escape exceeds the speed of light, which is the speed limit of the cosmos. Matter and radiation fall in, but they can't get out. Okay, so they talk about radiation, rays again, and that's why these people get in trouble, because they don't pay attention to the language. Okay, whatever radiation is, right? What is it, a ray? Is it a stick of some kind? Is that what a ray is, a stick? But that's what a black hole is. Essentially, it sucks everything inwards. That's what they're saying. And the boundary of the black hole is this event horizon. What's that boundary? Well, supposedly where the speed of light is, at that point, up to that point, it matches the speed of light. So anything touching that surface, even though there's not a surface, it's just like a boundary. I like to liken it to a campfire. You have a campfire, that's a singularity, right? And then you have the region of heat, where you can still feel the heat. And you can go farther and farther away from the campfire. At some point, you won't feel that heat anymore. Now you've got the cold of winter or whatever, wherever you're at. But as soon as you approach the campfire, right, at some point you start feeling the heat and say, okay, this is the event horizon of the campfire. Okay. The problem here is that in the case of heat, you have vibration of the air. So air is the object, the thing. And campfire is the singularity, but campfire is made out of wood or whatever you've got there. And in the case of this black hole, there is no campfire. It's zero-dimensional singularity. And that's creating this region of heat. Let's call it that way. Well, it's a region of gravity, right? And the question is, again, how can a singularity, which is absolutely nothing, no volume, no diameter, no radius, no shape, no size, no nothing, how can that create gravity? How can it have an influence on objects? Okay, we have a concept that has influence on objects. That's what a singularity is. It's a runaway mass. That's all it is, or that's what they liken it to. Okay, so here's NASA's version of singularity. Okay, let's see what they say about black hole singularity. Black holes form at the end of some stars' lives. So we're talking about a star, right? It's going to be collapsing on itself. The energy that held the star together disappears and it collapses in on itself, producing a magnificent explosion. Okay, so they're saying it's really an implosion, what they're talking about. It just collapses on itself, right? And it's going to form that singularity. All of that material left over from the explosion, many times the mass of our sun, falls into an infinitely small point. Okay, so they say, look, this thing is shrinking, 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 and falls into an infinitely small point. That's not true. Okay, it's not true at all. The so-called infinitely small point is really a zero-dimensional singularity. But they never say zero because people would say, well, what do you mean by zero? There's nothing there. And so they say it's infinitely small, and nothing, are not the same. They're not synonyms. Infinitely small says that if you still have Atom Man, he goes with his camera, he can take a picture of it. You cannot take a picture of nothing. Okay? You cannot take a picture of that which has no volume, no shape, no size. That's what a singularity is. But they don't say that. They say infinitely small point. And that's where the trick is. Okay? To escape the correct wording, and NASA is no exception on that. They tiptoe around the correct language. Okay, so here we have where is it? Here we have the Wikipedia version of that. It says the same in mathematics. A singularity is a point, right, at which a given mathematical object is not defined, or a point where the mathematical object ceases to be well behaved. So these people are talking about math. The other people were talking, the NASA folks were talking about a physical object. They're saying the star collapses to a point, or a small, very small, infinitely small point. These people say, no, it's a place or whatever. It's when mathematics dies down, where you get into infinities. And so they call that a singularity. So the question is, can we use this notion of singularity in physics? Okay, they're talking about math over here. The other guys were talking about physics. They're talking about a star that collapses to a point. These two are two different things. You cannot reconcile them. Either you talk about a physical dot, or you talk about math and saying, at that point we have infinities in numbers. Okay, so that's where the problem is. And so here we have, this is the Wikipedia. This is part of what came out of that article in the singularity, black hole singularity. It says, in 1924, Arthur Eddington showed that the singularity disappeared after a change of coordinates. Okay, although it took until 1933, listen to this, for George Lemaitre to realize that this meant that the singularity at the Schwarzschild radius was a non-physical coordinate singularity. So they have this non-physical coordinate, they have this star, they all know they were shrinking a star, but then they turn it into a non-physical coordinate system, where they say it disappears, whatever that means. What do you mean it disappeared? What did it turn into? Did it turn into space? But they say it's a non-physical one. And so if you're going to do math, don't bring it into physics. We either have physical contraction to a point, meaning a point that is still small, infinitesimally small, or you have numbers. So which is it? Are we going to talk about infinite numbers or infinite size? Okay, or infinitesimal numbers or whatever. Okay, so here we have Stephen Hawking. It says, oh, by the way, the black hole singularity doesn't only suck, it also spits, just like, the one that created the universe, the one at the Big Bang. Here he says, the following says, this is someone who quotes him, but it comes out of his book. I didn't have time to look it up, but I guess we can all do that. Hawking radiation is a theoretical prediction, all these predictions that the mathematicians make, by physicist Stephen Hawking. He suggests black holes are not completely black, but instead emit small amounts of thermal radiation. Radiation, is he talking particles? Do they spit out particles? No, they talk about radiation because radiation is a concept also, so they say it spits out concepts. Okay? According to Stephen Hawking, black holes can slowly lose mass and energy over time through this process, which is a form of quantum mechanical radiation, right, associated with the event horizon. So they talk about all these concepts, and so you get mixed up because they're not really talking physics. They talk about energy and mass and radiation, all these concepts. Now I want to know what it loses. Is it losing particles? Is that what they're saying? I thought the black hole crushed all particles out of existence, which is what they say. It shrunk to absolutely zero size, as Chandrasekhar proved mathematically. He got the Nobel Prize in 1983 for proving that the black hole, in other words, the star, collapses to absolutely nothing, no size, no radius, no shape. And somehow Hawking came up with some math where he proved that, by the way, that singularity that crushed every piece of matter out of existence also spits out what? Radiation and energy and mass and who knows what. Yeah, they're talking about concepts. So they're all sucking and spitting out concepts. Great. I want to see them do that in the lab. Okay, so what's the problem? Well, part of the problem, or a big problem of the singularity, is this infinity, infinitesimal. They use these words, whatever they mean in physics. And here I'm going to show you what they mean, okay? This is important to understand. The infinitely irrational world of math, that's what it is. And in one case, you have the world of the small, where you go to infinitesimally small, okay? And there you have my left to right infinitesimal sign. And then you have the infinitely big, which is the guy on the right, okay? And they put the singularity really at the infinitesimally small part. And why? Why do they put it there? Because they want to give you the idea that it's not completely zero, it's just very, very small, whatever that means. You know, it's just they deal with these size things. So they want to suggest to you that the singularity of a black hole is not completely zero, not completely no volume, no size, no shape. It's just small, very, very small. Okay, that's the issue. And yeah, mathematicians have these ideas involving infinity, in one case infinitesimally, and the other one infinitely. And they use these words, whatever they mean. And the issue is that you cannot use the word infinite in science because it's an irrational term. Infinite is the opposite of finite, okay? And all objects are finite. Every object in the universe had better be finite, in existence. And take any atom, hopefully it's finite. You know, it's got some size, some structure to it. And to say that this atom collapses to absolutely nothing, but it's still there, or its mass is still there, or whatever, it can affect something on the other side of the universe. Well, you know, you got to explain that. How does it do that? How does nothing do that? In fact, you know, how does it do it without anything between, you know, two atoms? How does one atom affect that one over there if it's got nothing in between them? That's one issue. The other one is if it's absolutely zero, singularity, how does it do it anyways? I mean, what do you have? You have nothing affecting something. So this is where the problem is with these singularities. And so here's the famous black hole picture that they took a few years ago. And the singularity is really at the center. So then why did they put that picture there? Well, they put that picture for people who don't know anything about, you know, what these so-called physicists are doing. And so they said, look, what you're staring at is a black hole. And people say, okay, I understand what a black hole is. It's dark in the center. It's got all this light stuff on the outside. But what the people don't realize is that that one in the center is zero dimensional. There's nothing there. That's singularity. That's the first problem. The second problem is that whole thing is not a black hole because, you know, where does the event horizon end? Does it end where you see the light still? And how can that possibly be? Because, you know, you shouldn't see the light at all. And so you have to think that the dark spot in the center is what the event horizon is, with a zero-dimensional singularity at its center. And the question then again is, what are we staring at? Are we staring at light falling into a hole in space, or are we having some other process there, like the one we suggest, which is that the magnetic field of the galaxy is moving stars around or creating that effect there that you're seeing there. So again, the question is can this be explained with mass? Okay, is this a question of gravity and mass that we're staring at there? Whatever they filmed there, whatever they took pictures of. Because again, if it's singularity is zero-dimensional, it's not part of science. It's not part of physics. That's how simple it is. Okay, so you cannot use the 0D concept and say that's what it has infinite mass and that's causing, other objects to move around, because that's the whole issue. Well, actually, you have two issues. One is, how does it affect another star? If it's just mass, if it's just a concept, okay? And then the other one, if it's zero-dimensional, it's got nothing there, how can that affect anything which is real, physical object? So you got two problems. The mathematicians have two problems to explain. And again, that's the circular argument that we've brought up several times. There you have it. The black hole is made of mass. That's all it has. Mass is the quantity of matter, okay? And defined as the quantity of matter or as the measure of the quantity of matter, right? It turns out that a black hole crushes all matter out of existence. So we have no matter. We have no matter. Hopefully we have no mass. And they say it's infinite mass in zero volume. That's what a black hole is. And that's the singularity, is the zero volume in the center. And so, yeah, we have, none of this makes any sense, but you have all these papers being written out there, published out there, where they talk about the singularity, about black holes. They're all investigating black hole singularities. And what they do, they take pretty pictures of something they saw out there, with, maybe with their telescopes, flying telescopes, and they just show you pictures and say, we're doing science. Yeah, I don't know. What have we learned? All they do is just put pretty pictures of movie stars. That's all they're doing. Okay, so here's the problem. Even if you have zero-dimensional and it's got infinite mass, okay, how does kilograms, move a star around itself? That's what you got to explain from a distance. You got mass, which is just kilograms, right? So how does that kilogram, just a concept, weight, essentially, how does it move a star from a distance? What's the physical mechanism? Because that's how they supposedly discovered the black hole. And so those are the questions that the mathematicians have to answer. What is a singularity? Does it belong to physics? And if they say yes, it does belong to physics, it's something we calculated mathematically, okay, no problem. We don't care how you came up with it. Could have been in a bad dream, no problem. The question is, what is it? And if it's zero-dimensional, that's one problem. And the second problem is, even assuming we give the infinitesimal dot, the small dot, how does it physically affect a star that's on the other, that's supposedly orbiting around it? And those are the questions for the black magic, actually, black hole singularities, the mathematicians. Those are the questions they have to answer.